Alors, on va continuer à rester au niveau macroscopique.
So, let us continue on the macroscopic level today. And gradually, we're going to move downwards to smaller scales as the lecture progresses. So this morning we're going to have the lecture followed by the seminar, and this afternoon a workshop, to which of course you are invited if you would like to come, which will be dedicated to this morning's topic. So those of you who want to continue or who wish to speak are more than welcome. Today we're going to talk about choice of materials. In the first hour, I'm going to tell you where we stand in terms of systematic choice methods, and also discuss recent changes, or relatively recent changes, which Stéphane Gors from Bordeaux will be telling you about during the seminar, and how these methods can be or adapted or ill-adapted to issues of choices of materials for functional applications. And this point of view will be illustrated. And this afternoon we shall be hearing about how materials can be developed with inspired directly by their actual method of choice. So we are going to move from design to manufacturing, because the materials are going to be developed in terms of the specifications and the choice itself. So I'm briefly going to take stock of what we are capable of doing currently in terms of systematic choice. So let me reposition this on my diagram as usual. We saw multifunctional architectured materials, and here we have choice of materials and processes, the art of compromise. And we're gradually going to move across these blocks here, go down to the microscopic level and then back up to the macroscopic level, and we'll finish with bio-inspired materials. So, the art of compromise. So, obviously, the choice of materials didn't start in the 20th century. I started my inaugural lecture by talking about prehistoric times, when they noticed that they should use a flintstone rather than a limestone to make a tool. So it was trial and miss. What is new is how a certain amount of information can be structured in order to manage this problem with hyper-choice, the fact that you have somewhere between 50 and 100,000 materials to choose from. And to have a systematic choice, not something that means that you don't need to think anymore, but to automate the process in order to stay innovative, both in the design or of materials. So Michael Ashby developed these methods around 20 years ago in Cambridge, but it was actually a long process. Mike Ashby actually is an extraordinary person. When he started something, usually people said, no, things are much more complex than that. But in fact, his innovations have made it possible to save a lot of time. Mike Ashby had created a materials database around 20 years ago because he'd worked on metals and ceramics and polymers. And initially, it was a very primitive selection tool. Basically, it was just a database with a few materials in it that were representative of their class, and a very visual tool that allowed you to enter 1, 2, 3 criteria in order to choose them. Things have moved on significantly since then. The software is now public domain. It can be used either in a generic version or in specialized versions in the corporate world. So the latest one is called the CES, Cambridge Engineering Selector, which is updated every year. You have, of course, the material selection process with very large databases, hierarchy, no gaps, properties that are not known can be estimated. There are databases of processes and their various attributes. What materials can they be used with, in what geometries, what rate. There's also a cost estimation tool. We'll discuss that later. How you can choose between the most cost-effective process. In recent developments, there is now also a eco-audit tool to assess the environmental impact. There will be a lecture specifically dedicated to the approach and its limitations. And final characteristic is that now you can have tailored databases. So I'm supposed to tell you about science in the making. Perhaps this is, it seems finished, but I will tell you how there are limitations to this. So the three questions we're going to be discussing this morning are: how can I choose the best material for a given application? Second question is the reverse of that. I have a material, what can I actually do with it? Because labs have lots of materials that just stay stashed away somewhere. But usually materials are not used for a particular property, but for a whole set of properties, which needs to take into account specifications. And one of these specifications is how they can be implemented. High temperature superconductors would be much more effective if cables could be made out of them. So I'll try to show you how you can turn the question around about what you can do with a new material. And then I shall finish the lecture by opening onto problems of optimization. I'll show you that there are a certain number of issues that are also very important. What tools can be used to find your way around a very specific space of optimization with separate names of materials, but it's also continuous because there can be compositions that are continuously changing, dimensions that are continuously changing. And that leads us to have rather specific optimization tools, and plenty remains to be done in that field. So, the outline of the lecture, I'll tell you about the general wisdoms in selecting materials. Then I'll tell you how these generic methods can be adapted to produce specific tools. Then how can you find an application for a given material? I'll discuss the various strategies. I'll then start to discuss the touchy stuff. The touchy stuff is when you're trying to design with durability in mind. And I'll show you what we know how to do and what we don't. It's actually very rare that engineers design stuff that's only going to work once for 5 minutes. So questions of durability are very important. And it's one of the tough points in these approaches. Then I'll try to discuss issues with optimization. We'll finish with an example where I'll tell you how you can use specifications to develop a material using these selection methods and materials development processes, which is gradually going to bring us to our final example. It's conductors that you use for high magnetic field magnets, and I will show you how the material can be manufactured based on the specifications, which will allow me to yield the floor to Stéphane, who will tell you about issues about materials choices or material development from a more functional point of view. And the conclusion will be where we stand. I won't tell you where we're going. So, generic methods. The basic idea here is to give a great freedom of approach, that you can select your materials with very broad options. The basic idea is that there are problems of comparison between the various materials, and these are questions that need to be asked in the very beginning. That was one of the big problems with some composite materials. People said, okay, I'm going to make this part in metal, and then I'll go and see someone from polymers and say, could you make this with a polymer matrix? When you're trying to make a bike frame with a polymer matrix composite, you redesign it. You don't make it. It's, you know, there's the sort of diamond shape that you're all very familiar with. If you make a composite frame, you have composite tubes, of course. And then what do you do with these composite tubes? You need to assemble them. And assembling tubes made of composite materials is a total nightmare. You just shove them into metal bits, and then your metal frame is much too heavy. If you really want to make a lightweight polymer matrix carbon fiber bike frame, you need to design its geography first. So it's a question you really need to ask upstream. These are really very basic ideas, but you need to avoid the impasse. The second one idea is that comparison between materials requires very precise specifications, and you need to see what is a constraint in the specs and what is an objective. It's very rare that you ask a structure to be as rigid as possible. It's just asked to be sufficiently rigid, or as cheap as possible, as lightweight as possible, and so on and so forth. Sometimes you actually over-specify. That is a risk. So you really need to make a difference between constraints and objectives. Another important thing is to look at the relationship between these various constraints, and to try and get a very clear idea of what is negotiable and what is not. I will show you a couple of examples of that, and when we discuss optimization, I will show you how you can discuss, obviously, a key question, which is how can you have a multi-criteria selection. There's another very simple idea, is that when you have a multi-criteria process, it can be multi-objective or multi-constrained. Multi-constraint would mean you say, I want something to be both rigid and solid and robust. So you need to say, what is the most difficult thing to achieve there? So you need to analyze what constraint is going to limit you. If you say, I want it to be lightweight and cheap, minimal mass, minimal cost, the first question is, how much are you prepared to pay to make the structure light? So the rationale here is not about the limits. The rationale here is about the trade-off between various objectives. And that's another important point. And final point, a third point that's actually very important in selecting process, in the selection process, you must bear in mind that it's an iterative process. You have your specifications, you have a certain number of choices in your selection choices that are going to lead you to redesign part of the specifications and say, okay, I'm ready to give up on this as long as I can gain on that. So it's an iterative process. It's not at all a type of process where you enter specs into a computer and the specs come out on the other side. Things don't work like that. It's an iterative process. Specifications which are constructed, rewritten as you move on. Final important point, you need to select a material, but you systematically need to select material, shape and process. Let me take a very common example, just to show you that in very widespread objects, there's a lot of innovation. Take an alloy wheel, for instance. You could say that the wheel can be made of steel, or it can be made of aluminium alloy. It's called alloy wheel. It's called alloy wheel, as if steel was not an alloy. Of course it is. So you can have either a steel or an alloy wheel. What you do is that you take sheet metal, you punch it, you roll it up, and that makes a steel wheel. If you want an aluminium one, you cast it. You cast aluminium into a mold. And what you obtained is something that's molded rather than die cast. So if you come along and ask someone to make an alloy wheel out of steel along the same model, it won't work because it can't be cast. So the question of knowing whether you're going to be using steel or aluminium makes no sense if you don't ask at the same time how you're going to make it and what shape it's going to have. The aluminium alloy wheel is much thicker and can be molded, can be cast. So then the question of, is it going to be heavier if it's steel or aluminium? If you look at the properties, you'll say it'll be lighter if it's made of aluminium. But if you look at the process, you will see that in fact you need to have much thicker parts. And in fact, an alloy wheel is usually much heavier than a steel wheel. So why do you actually buy alloy wheels rather than steel wheels if they're heavier and more expensive? The answer is very simple. The answer is that it's prettier and it doesn't rust. So another whole new set of criteria. All of that to say that processes, materials and shapes go together and they're not systematically treated. They need to enter gradually within the selection process. So this is a diagram here of the various phases in the process. Try to find a more widespread example. Say that you're trying to recruit, you're trying to hire someone. So you have 3 steps: screening, ranking, and documentation. To the left of the diagram, so what do we mean by screening here? And ranking and documentation in terms of materials. On the right-hand side, left-hand side, your material selection, right-hand side, process selection. So you're trying to hire someone who works in mechanics and materials. Your applicant is a dentist, but he doesn't have the skill set I'm looking for. So, first step of screening, for instance, if you're working with a material, you say, okay, this material needs to operate in an aircraft engine and needs to withstand temperatures of 800 degrees. And that allows you to screen out a certain number of materials that don't stand a chance. And in the same way, you can use processes too. If you're going to make the Eiffel Tower, you're not going to do it by a vapor phase, atom by atom production. So you can say such or such a process does not allow you to obtain such or such a size or shape, and such or such a material does not have the required properties. So your screening has kicked out your dentist. So you say, I want someone who's both good at mechanics and good at materials. I have loads of guys who are good at mechanics, loads who are good at materials. I need someone who does both. So what I do is that I then rank by a performance index. And the simple idea is that the index is the combination of properties that make a material relevant for a given shape, a given load, a given stress, and a given objective. And that's what we're going to call a performance index. So you have pulling, something that needs to be very rigid and very lightweight, a type of constraint. Well, the property that characterizes the material's relevance is its Young modulus divided by its density. It needs a high modulus and a low density to obtain these properties. But things are actually very explicit. It's E divided by O. It's very easy. If you have the same question for something where flexion is required, it'll be E to the power of 1/2 divided by O. So you need to find the match between your material and your specifications. So for a physicist or a chemist, a material has properties, and for an engineer, a material has performances. In terms of the processes, what's going to be involved here is going to be the cost estimate. Depending on the number of parts you need to make, the shape you need to obtain, you'll say, I'm going to use such or such a process. So the classification tools on the materials side, you have performance index, and process side you have the cost, and then you have the documentation step. So you've seen a few interesting applicants. You're going to say, are they team workers? Do they tend to boast about things? A lot of interesting questions. Some questions that you're not going to be asking about the dentist, of course, because the dentist didn't stand a chance from the start anyway. So questions such as, do I know how to solder aluminium alloys? Does this resist corrosion? These types of questions need to be asked about various applicants who potentially are interesting materials. So one of the limitations here is that every time you have a sort of system-based question, something that's not just the material itself, but stress, for instance, problems of friction, for instance. Every time you end up in that sort of situation, if it's a complementary information, you'll know how to process it. If it's essential to selection at the very beginning of the selection process, that is a difficulty when doing systematic selection. When you have a systems approach issue, they're very difficult to process upstream. So let's now have a look at the state of the art and the limitations. So if we look at the tools to compare materials, you have the performance indexes. When you compare the processes, I'm just talking about estimation. I'm not saying how much the car door is going to cost. I'm not saying what the dimensions of the part are going to be. What I'm saying here is, based on the specifications, this material stands a better chance than that material. Another important problem is multi-criteria, optimization methods. I'll tell you a little bit because about this. There are systematic methodologies. Another tool you need is databases that can be in the public domain, and the Cambridge software, or they can be from the private sector. There are databases for Schneider Electric now, which are designed along the lines that I'm explaining. And then, of course, all of this needs to be implemented in the shape of software that can be used by product designers. That is the final step. The most important thing is not so much to have the actual tool than to have the structured systems allowing you to source the information. So, the indices I was telling you about earlier. What we're trying to do is to find a combination of properties to tell you how well a given material can fulfill its task. So you identify function constraints and objectives. If we look at our tie rod, for instance, you have the length that is specified, and it must not fail under such or such a load. You have minimal mass, and your free variable is the size of the rod and the choice of the material. So, if you want to enter the objective, you have the mass, which you wish to minimize. You want the constraint to be lower, that F divided by A be smaller than the elasticity limit, and between the mass and the constraint, but that must not be higher than the elasticity limit, you can see that the mass of the part you're looking for must be greater than the force times the length times the density divided by the elasticity limit. A bit of algebra there, but what's interesting when you write this down, it's like the Stoicians, there are things that depend on me and things that do not. What I'm in charge of is selecting the material, and what I cannot select is the force and the length. So this here needs to be minimized, and that results in a performance index that says the highest performance in terms of my objective of minimal mass and the constraint is the one that maximizes the elasticity limit divided by density. So if you want to have a look at the various parts of your bike frame, you have the strength specified, minimum weight. Now, if you actually want to have a beam here, you want something that's stiff. You still want minimum weight. What's going to be important is the e to the power 1/2 divided by density. I won't give you the details of this algebra, but if you say that it is limited by a strength, I would see that the performance index, if I want to minimize the cost, here it's the material cost, not the process cost, you have the elasticity limit to the power of 1/2 divided by density. So how can you describe indices that gives us the relevance of materials for a given point in the specs? So I showed you this map before. You take the Young's modulus graph, you trace logarithmic lines here of equiperformance. So if you have modulus divided by density to the power of 1/2 or to the power of 1/3, if you were working with plates, and for each of these lines you have materials that have equal performances, that are going to have the same mass for a given strength. So that is the basic tool to allow you to compare materials for pieces of the specifications. Now, if you're examining the processes now you have the size, the type of material, the rate of production, and so on. Typically, you take a pencil sharpener. If you have just one pencil, you use a penknife. If you have several pencils, you use a pencil sharpener. You have one with a handle. And if you make pencils, you have a robot to sharpen your pencils. It all depends on the scale that you're going to be producing things. So in fact, the cost model is actually quite simple, because you're just comparing solutions. You're not just saying, I'm going to be selling my car door for such or such a price. So in order to compare solutions, you need to have the material cost, and perhaps loss of materials because you're machining. Here you have the tooling cost, which you need to divide by the number of parts you're going to be making. And then here you're going to have the production rate here. Obviously you sharpen more pencils with a robot than by hand. And that gives you a cost estimate for a given part. And you can see here, based on the cost, to obtain the same part made of the same material, you can either machine a cast, you can cast it on the plate, or you can cast it by compression. It's a polymer plate here. And if you look at these three costs, you will see that cost per part, it's better to machine it if you have very few. If you have a bit more, let's say more than a dozen, it's better to have compression molding, or casting if you have more than 1,000. So these are tools that are actually going to help you to choose such or such a production process. So a software is actually based on very simple things, and if we look at the state of play, based on databases that have a certain number of common criteria, you try to find a unified, homogeneous approach. There's a hierarchy within the databases. There's a tree structure. You have metals, you have steels, and then you have low carbon steel, stainless steel, and so on and so forth. You have a hierarchy. And as I was saying, the selection process is iterative, meaning that you're going to have quite a sort of rough hierarchy, and you're going to go down deeper into the tree structure to choose between various types of steel, various thermal processes, heat processes. So you try to remain objective here. you try to minimize non-objective intervention. As long as it's possible, you try to avoid weighting coefficients. Ultimately, you do need to do it, but I'm going to show you how you can delay that as much as possible. And then, of course, one of the benefits of this database is that you have a database, you just draw lines, and you can do that with a dozen criteria. You can already have a multi-criteria selection without weighting the various aspects. That's just one part of the story. CES software include around 3,000 materials, around 50 properties, quantitative, qualitative, or Boolean, with an acceptability range. Qualitative will be it withstands well, not very well, not so well, not well at all in salt water, and Boolean will be I know how to solder it or I don't know how to solder it. So there are going to be links to the processes here. The information system has all sorts of processes and all sorts of materials, and you'll say, okay, such or such a material is possible with such or such a process. Then in the process database you have around 800 processes, and the equivalent of the properties here is attributes. The size, the roughness, the fine forms that you can create. There's economical data to allow you to have a quick cost assessment, and then you have links to materials and possible shapes. So the different specializations that have emerged in recent years is the possibility to have functional dependence. It's not just a property per se, but a property that depends on the temperature. You can have a database that has functions of properties. That's what Schneider Electric does for circuit breakers, for instance. You can have specialized databases. I'd even actually made one to select wines based on cheese. It's actually very similar in terms of process. And that is the state of play of current software that exists in the public domain. There's a cost estimator. You can have specialized databases on both sides. So obviously now, CES software are very effective in the first stages of design. They are very flexible types of sets of requirements. When you have complex materials, for instance, time-dependent design, wear, creep, corrosion, fatigue, if that is your key pre-definition criterion, these tools do not work very well. If you have very complex coupled process requirements, you need to be much more specialized. Just to give you an example, when choosing materials for molded aluminium objects, you need to see what depends on the part's geometry, the part's shape, and that can only be done specially for the various classes. So you really do need to go much more into detail. When you have information that is unstructured, that is much more an issue of looking for information and that is much less specialized. Hence the following step. I showed you the rationale behind the generic software. How can you create specific software? And one of the problems is that when you want to be specific, it becomes confidential. Obviously, Schneider Electric is not going to upload to the web. It's a polymer selection tool for circuit breakers. But let's have a look at the information here. I told you about the numeric properties, and in a sense what I call non-numeric properties. That is basically what you can find in CES software. But when you have design guidelines, case studies, failure analyses, established applications, what does this new application look like compared to existing ones? FE modules, what I showed you in terms of performance index. You can very well couple that with finite elements calculations for performance calculation. So all of that will be much more of the non-structured information type. So, specific methods of choice. In the same way as earlier I was telling you that systematic freedom, systematic methods give you freedom, specific applications gives you memory, and we're increasingly in cases where you're not only storing data, you're storing know-how, expertise. There are three key strategies. The first one I have already told you about is the free research with the performance index, databases. The free search, you have a lot of freedom, but very quickly you're going to be restricted in your design. Another strategy is that of the analogy. This design looks like that design, I've done this or that before, and therefore I can use that particular idea. That can be very efficient or very restrictive. You can become very conservative or even mess up. A good example of that is selection of materials for typewriter balls. I don't know if you... They call them computers without... Kids call those computers without screens nowadays. So, of course, initially you had these little arms with the letter on the tip, which is why we have these weird keyboards, because secretaries type too quickly, and the little arms used to intermingle, and that's why the letters are in such a weird order. Then there was a little ball that could rotate, and then to print the sheet, because it avoided the problem of these little arms getting all muddled up. But the ball itself, the question was, what should we make it of? IBM, pretty smart guys, but the first ball they made was made of lead. They thought, okay, printing, typeface, typesetting, lead, let's make these balls out of lead. But what you wanted was something that has, of course, a very low inertia, and that is not too soft. And obviously, lead was probably the worst solution possible. And if you find lead typewriter balls, they're really collector's items. So they really quickly moved on to other materials. But working through analogy can actually restrict innovation or even lead you to mess up big time. So I think that is probably something that has not been explored sufficiently, but it needs to be explored carefully. What I really want to tell you about is the questionnaire-based approach, based on expertise capture. Let's look at aluminium alloys and see how the question emerges. When you've selected something for a cast aluminium part, you have technical questions: size, weight, max thickness, finish, processability issues. You have what are the fill line features, and obviously if it's aluminium, you need to avoid hot tearing. There are questions of properties. You're asking for tensile strength, ductility, and then you have economic issues based on the batch size. So when you start working on this, when we started working on this, we worked with a casting expert who worked for Alcan. And when you're talking about performance indexes, he says, okay, this is my performance analysis, and invariably it was aluminium copper. He said, yeah, you're quite right, except that I have no idea how to make this part. So the limitation here, once you decided to the aluminium alloy, was not the properties of the material itself, it was the processability of the material for a given shape. So we had to change completely. The idea was no longer to have a database of properties, but of expertise, where you could store information about the fact that such or such a shape can be made or cannot be made with such or such a process or alloy. So obviously, we're actually going to have a look at a couple of cases. All of this, of course, is not public domain. This is storing a corporation's know-how in order to systematically have a quick analysis or even train new engineers. So let's look at the filling index for an alloy, how the mold is filled. You semi-solid, see the constraints, see when there's going to be tearing. These are very interesting scientific questions that have not yet been solved. An alloy, as it is solidifying, its properties are, is still an open question. However, parts have been manufactured. In order to make that, you're going to try to archive the know-how. If you make a given part, you can have characteristic length. If you look at the various alloys, you obtain nomograms. When you have one where the creakability index with an indice D, it will tell you that with such and such a process, you will only you can only create thicknesses that need to be higher than 4.5 millimeters. So you could probably dream of predicting that. Perhaps in the next decade it will happen. But for the time being, you just need to store this expertise. Then if you take another type of alloy, here, if you have a type 4 alloy with a castability index here, it's going to tell you that for the same thickness, for the same part, you're going to be at least 5.5 millimeter thick. So what do? You have dedicated tests. You pour the alloy in a kind of spiral and you see how far it can go down to fill a mold. And that is how you can read processability features for such and such an alloy. You can do that for mold filling. You can do it for a certain number of processes of processability aspects for a given material. I'll try to speed up a bit here. How much? 20 minutes. Yeah, I'd better skip a few things. I just wanted to show you here how a given expertise could be stored for a given process. Another example is choosing joining methods. Here it's a tool that allows you to select experts rather than processes. If you go and see someone who does welding, someone who does mechanical joining, someone who does gluing, they'll always find a solution. The idea now is to see upstream who you need to go and see. And you're going to use a type of questionnaire. This will be done with the city in Saint-Étienne. You're going to have questions about available shapes, the types of solicitations of stress, whether assembly is done in a clean room or on site. All of this is going to direct you, orient you towards a certain number of acceptable processes. And then you can go and see the experts in order to create the assembly. So, if I talk about the state of the art and limitations, you have generic tools that are well adapted to the initial stages of design. If you have time-dependent issues, we're not very good at that yet. If you try to compare materials, it's performance indexes, usually. If you look at forming properties, you need to store expertise information. And the lower down you go in the selection tree structure, the more you need dedicated software solutions. So let me now discuss something else, the issue of the reverse question. I have a material, what can I do with it? I think that can actually see condition how you look at a new material. So these are the types of strategies you can implement. So remember, you say you're looking for a material, you have specs, and you try to find the material that seems to fit, seems to be the best fit. So you would think that the reverse would be you have an application database, you take a new material that has such and such properties, and you look at the type of application that is the best fit for the properties of the material, and all is well. Except that things absolutely do not work like that, because a database of applications is a true nightmare. I still have no clue, I don't have a clue of how to make that, and specifications are not detailed enough to create a generic application database. So forget it. Another strategy is to say, okay, this material I've just invented or discovered, amorphous metallic alloy, say, what are its properties? There you can say what are the main interesting properties or performance indices. If you look at amorphous metal, solid amorphous metal alloys, the fact that it's solid means you can make thick parts. The crystallization temperature is quite good. There's quite an extensive range of shaping options. So the properties are interesting based on its capacity to be shaped. So if you look at this alloy, you have an elasticity limit, and you can see that the ratio between the modulus squared divided by the elasticity module is particularly interesting, meaning that you have a performance index database here, and you say, oh, this material looks like it might be interesting. The square of the modulus divided by elasticity limit is see how you can store a given property within a volume unit, meaning that this particular material might be interesting to make springs, small springs, not necessarily low mass springs, but that sort of turns you towards a given application, where you can say that this amorphous alloy might be interesting to make springs. Springs may vibrate, so you need to know things about fatigue. If you don't know, if you don't have that data, it's worthwhile to examine behavior to fatigue. So you can have incomplete knowledge, you can see possible applications for a particular material and try to investigate further properties to see whether it's suitable or not. And that is what I would call functional search. Function search. So in order to do that, you need to have an indice database, and for a new material, say what would make this particularly interesting. And that can give you ideas of possible applications. A final solution is the cuckoo material. How does this material look like other existing materials? You need to have a distance in the space of materials. It's actually quite easy to do. You just have the difference between a property of material X and the same property in material Y, average that, square it, and you have a distance that says such or such a material is relatively similar to that one, and this material has such or such a type of application. So you can go and have a look and see whether perhaps you could not use it for this or that type of application, except that this distance that you've defined is completely arbitrary. So if you have a potentially similar material with a potentially interesting application, you need to redefine a distance which does not take into account anything else than the properties that are relevant to the application. And you can look whether the new material is similar to the material you want to compare it with. So it's not a systematic method to say, okay, this is a sure hit, but it kind of helps you to find your way in the jungle of potential applications. So again, this was also developed in the form of software, and that's what I call the reverse process. So, durability issues. Just to say a couple of words about that. It's tough. the durability of what you've chosen. How long is this thing going to work? It's very tough because it's actually very difficult to obtain the information. If you take corrosion, it's very difficult to have a database where you have all of the data of all materials in all environments at every temperature. So information difficult to get, and even if you do get it, it's not necessarily the information you need. For a given material, it's quite good to have sort of data about generalized corrosion, but maybe that's not your problem. Maybe it's localized corrosion. Things need to be approached systemically. If you take a tank that is corrosion resistant, a water tank, say, the first thing to do is to avoid stagnant water. So you need the bottom to be sort of rounded rather than convex. And so these things are not easy to assess. And then problems of choice become dependent on dimensions. If you want to have a pressurized tank with water in it that needs to withstand corrosion, it's not the same thing to do it for a small model steam train or for a large, full-scale steam engine. Perhaps it's not technological innovation, but you will feel that based on the size you're trying to achieve, the choices are different. It needs to withstand a given pressure, your little steam tank. If it's thin, you need to have something that withstands corrosion much more than if it's a good thick layer of ductile steel. I'm going to show you a couple of performance indexes here, indices, that have been calculated for problems of generalized corrosion with various types of constraints and the analysis. So you have here a rod where you want to minimize mass. I was saying it was modulus divided by density. But now, if you want to add to that generalized corrosion, so it's actually becoming smaller, it's shrinking, and obviously that means you're increasing the constraint, and that means that things are going to go pear-shaped. And you see, if things don't last too long, it's not much of an issue. If it lasts for long, is what is the actual speed of the thinning of the part. So this is exactly what this indice says. Performance indice for this particular situation is the modulus divided by density, divided by this horrible little formula here, where here you have a constant which is the material erosion constant in an aggressive environment, and you can see here the time that's factored in, the time for which the part needs to operate. So if it's very brief, you just have E on O, and if it's long, you just keep the second one. You see that the E will disappear and you'll have something that is just going to give you the rate of corrosion. And what this approach says is that if the time is somewhere in the middle, how do you weight corrosion resistance and mechanical resistance? So it's a very simple case, but just to show you how you can assess durability issues when the information is available. So, questions of optimization. So, multi-criteria, multi-objective. When you have multiple constraints, which is the most limiting one? When you have multiple objectives, what is the trade-off strategy? What we're going to see are techniques that are starting to look very much like applied math. If you look at a multiple constraints issue, you want to have something that is both stiff and strong. The simple formula shows that mass must be a minimum this and limited by this, and you need to find which one is the most limiting out of these two. So when you equalize that, it's going to give you an area in the material space within which you're going to have an equal limitation between stiffness and strength. If you're in one part of the space, you're going to be limited by stiffness, or in the other part of the space, limited by strength. How does this look like graphically? This is the graph. You have your two performance indices here, M1, M2. You have the coupling line here, where the limitation is equivalent. If you're in this area here, you are limited by M2. If you're in this zone, you're limited by M1. So if you're trying to compare materials, which would be difficult if you hadn't weighted them, A, B, C, it would be difficult to know which one's the best. But now, if you do it like this, you'll be in a position to say that this material here is limited by M2, and so on and so forth. So you can actually rank the various materials based on their relevance to specifications. You can now actually say what the limitation is. But then that also depends on size. If you have a short or a long part, the question of resistance to flexing, stiffness, etc. will not be the same. You're going to be in a situation where you can no longer select purely without taking size into account. When you have contrasting objectives, things are a bit more complex. You have the mass performance, you have the cost performance, and you have the Pareto front, with solutions that are not overwhelmed by any other solution. So in order to select between those, of course you can, because if you're not on Pareto's front, you're sure that it's not going to be an optimal solution. So they are all optimal solutions, and therefore you need to assess the trade-off between your two objectives. So if you want to go deeper, you say, I have a trade-off factor, which is how much am I prepared to pay to reduce mass. So you have a combination of mass and cost and a trade-off factor, which says I'm prepared to pay such or such amount of money to save 1 kilogram. So in addition to your Pareto curve here, you have a tangent between equiperformance and the front that's going to tell you what the optimal solution is. It sounds very simple, but how do you actually build these trade-off factors? And that's a big problem, because first of all, people don't really want to tell you. Just to give you a couple of examples, you can have value analysis. You say, if I save 1 kilo on a car, and the car is going to be on the road for 300,000 kilometers, how much petrol am I going to save? If you do it on a plane that's going to fly back and forth 3 times over the Atlantic, and it does it all year round except when it's on the ground for controls, and you know that a passenger plus the seat plus 1/10 of the air hostess plus luggage at around 500 kilos, you could say, okay, I'm going to save 1/500th of a passenger when I've saved 1 kilo on the aircraft, and you need to see how much you're prepared to pay for that. So with this value analysis, you can have estimates of the various costs per kilo. So this is all a very rough estimate, of course, because that would mean that your airline would tell you how much money it makes per passenger, and they usually don't tell you. But these rough estimates are actually give you a pretty good idea of the trade-off, the potential trade-off. If you have something that increases the price of a car of more than €6 per kilo, it'll be tough. But if you're making a space vehicle, you can go up to $10,000 per kilo. So it can be done just by examining the market. I had done that with skis at Decathlon, the sport goods retailers. You saw the decrease in price versus weight. You can see that people are prepared to have much lighter skis for certain applications. So you can analyze the specs, analyze the market, and that gives you the trade-off coefficient. So this, I actually don't have time for this, but I'm now going to show you how you can use tools to develop materials. So we're going to try that for a given application, which is no longer a structural application. There is a structural application, a constraint, of course, but let's say that we're trying to make high-field magnets. They're usually magnets that are used for research, but you do need to make them. If you go to a lab in Toulouse, they can show you a museum of horrors, which is all of the magnets that exploded, because when you have a magnetic field, you're creating huge energy, and per volume unit it's something that varies like the square of the magnetic field. And when you have 10, 15, 20 Tesla, confining it within the magnet is something that's very, very that comes with very, very high magnetic pressure. So one thing that you need to do is to contain this magnetic pressure. You could write, such as here, the field you're trying to obtain squared divided by something that's a function of the geometry of the number of coils, diameter, and so on and so forth. And this thing needs to be smaller than the elasticity limit. It needs to be lower in order to produce the field. But then, of course, when you're doing that, you're creating a current pulse that's going to heat the material, and then you have a maximum admissible temperature. Your coil should not melt. Obviously, things are going to work not so well if that happens. So that gives you another limitation here. You will see that you have the elasticity limit, and here you have something that contains conductivity. Letter rho here is electric conductivity, and then the calorific capacity too. And once you have all that, it gives you two performance indices. One, which is merely the elasticity limit, not very important here, and the other one is the calorific capacity and density of the material and electric resistance. So if you look at various types of materials, various types of applications, either you have a very short or very high field, either you're going to be limited, restricted by mechanical resistance aspects if you have a very strong field, or heating if you have a very long pulse. So which material is preferable for which application? So things can be improved slightly. You don't just look in your CES database, you look in something slightly more specific based on these various indices of various types of fields you're trying to obtain, or pulse lengths. You have not just copper, but you have copper chrome, copper silver, copper beryllium, or materials that have been developed for that, which are composites. Copper silver composite, or copper nobium. Let's take two examples. Nobium is a superconductor, which is always helpful, and copper silver is easy to make just by solidifying copper silver alloy. What you have here is the manufacturing process. You mold, you have solidification here and co-extrusion here. What you're doing here is that you have copper wires, silver wires, put it into an extrusion machine, and you start again and again and again. You have this superb structure, which is wire, 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 wires, and you can do it as often as you like. You have here 50 nanometers, it's very small, an extruded part started by a directionally solidified alloy, and you thread it to reduce its size. And once you've done that, you end up with structures that are sort of a dozen nanometers of silver thread in copper. So processes here to create composites, and very tough, very hard composites. And they're very hard because they've been deformed extensively. But here, what is the initial scale? How much are you going to deform it? So in order to go further, you can say, okay, if I reduce the spacing between the fibers, I'm going to harden the material. So the elasticity limit is going to vary along these lines. Here you have the initial spacing in our solidification. It's going to be related to the solidification speed, and here you have the deformation. The more you deform, the more the elasticity limit grows. But then the more you deform, the more the spaces where the electrons are going to diffuse are going to be closer together, and therefore you're also going to be increasing electric resistivity. So you're winning on the one hand, but losing out on the other hand. What the modelling says here, that on more or less deformed copper-silver, is easy to understand. It's a very simple model. You can say that you can't do both things at the same time. You need to optimize. So for this particular criteria, you have copper-silver or copper iobium are good, and you need to have such or such an initial spacing. You need to deform it with such or such an extrusion process to obtain a material that is the best fit for a long pulse magnet or a high field magnet. So, my conclusions. The generic tools are available and usable in the initial stages of design. Specific tools can be well adapted to later steps, but they become specific, and therefore they're less and less public and more specialized. Time-dependent properties are something that is not very well mastered. There can be also an approach to help you orient the type of information you're looking for a given material. I also tried to show you that it's now possible to couple very simple modeling, property modeling approaches with specifications that are being translated in terms of performance through material choice. We're increasingly moving towards specific tools. You will find that also on the slides. And there is a set of specific tools that exist, and there are a lot that I've not included here. Luminex has a tool where one of the criteria is, can I paint this polymer with red paint, no orange paint, because you need to have a trademark placed on a different part. So a lot of companies, of corporations, have their own tools to help with material selection. A couple of words about nuclear. This can perfectly well be adapted to something that is very not merely mechanical. If here you want to make a combustible fuel rod holder, for instance, you could have something where neutrons go through it. If it's very thin, it would withstand the pressure within. So it's better if it was thick. You have a performance index, and the performance index says that you need to find something that maximizes, something that has mechanical resistance to a given temperature, resistance to creep, or capacity to absorb neutrons. So obviously you won't find that in standard software, but you can very well go find that in Neutronics manual, and you will see that there are a certain number of possible properties. It's not going to tell you whether you should use Zirc alloy 4 or another type of alloy, but based on the conditions of operation, it might be a good idea to go and see a zirconium or stainless steel aluminium alloys. You have other absurd here, magnesium in hot water, probably not a good idea, but it gives you an overview of the options. And I'm not saying that you don't need to go further, but it allows you to rationalize a certain number of things that you can start to explore. So, performance indices, and then I shall now yield the floor to Stéphane. Where's he gone? What direction do we go when we want to go beyond these structural performance indices? And beyond the standard tool, can that be seen as a guideline for materials development? Rather than say, I'm looking for a material for a given property, you can say, I'm going to develop a material for a relevant combination of properties. Thank you for your attention.
Hein